Hello everybody, welcome back to Physics 331. What the plan is for today's video is to try to finish off our discussion of Fourier transforms. So I've written down here, just as a reminder, what the Fourier transform and inverse Fourier transform are. The Fourier transform takes a function f of t and converts it into a function of f hat of omega in the frequency domain. The inverse Fourier transform does the opposite. If you know the f hat of omega, then you could apply the inverse Fourier transform to construct the f of t in the time domain. In the last video, we did a few examples where we worked with this. So for example, we imagined we had a square pulse in time. And when we took the Fourier transform, we ended up with this sinc function in the frequency domain. And one of the nice observations we made is that the narrower the pulse was in time, the broader the range of frequencies that are contained within the Fourier transform of that signal in time. And of course, the opposite is true. If you have something that's very long in the time domain, is very sharp and it has only a narrow range of frequencies in the frequency domain. We took that to an extreme where we imagined delta function pulse, so a pulse that is infinitely narrow. And when we took the Fourier transform, we got a frequency spectrum that was completely flat, and so all frequencies contribute equally to, are contained equally in the Fourier transform of a delta function. We then took that flat frequency spectrum and took the inverse Fourier transform, and what we were able to do is come up with a way of mathematically expressing the delta function. Okay, so what I want to do today to finish off this discussion is to just state some properties of Fourier transform. So some of these I'm not going to approve because you'll prove them in an assignment. And then one property we'll talk about in more detail and we will work through a proof. Okay, so properties of Fourier transforms. Alright, so the first one is, let's imagine that g of t is equal to some function f of t except the time coordinate is shifted. So we take our f of t function and express it as f of t plus b. If we do that, then when we take the Fourier transform of g of t, we get g hat of omega, and that's going to be equal to f hat of omega, the Fourier transform of f of t, multiplied by e to the I omega times b. Okay, so that's like a time shift property. The second one will be like a time scaling property. So if g of t is equal to f of t except we scale the time coordinate by some constant value a, then the Fourier transform of g of t is equal to the Fourier transform not of f of t, but, well, in fact, I guess it's not equal to f hat of omega, the Fourier transform of f of t, but it's equal to f hat of omega divided by a, and there's also a prefactor of 1 over a out front. Okay, and the way you're going to prove these is just to actually write down the Fourier transforms of, say, for the first case, f of t plus b, and then maybe make a change of variables, and the same thing for the second property is you'd write down explicitly what the Fourier transform of f of a times t is and make a change of variables, I think, is the strategy. Okay, the third property is let's imagine that we took the Fourier transform not of f of t, but of its time derivative. So this notation, what I mean is the Fourier transform of f dot of t, which is just the first time derivative of f. Okay, so explicitly what that would look like is the integral from minus infinity to plus infinity of f dot of t times e to the minus I omega t dt. And what you'll prove is that's equal to I omega times f hat of omega. So f hat of omega being the Fourier transform of f of t. Okay, good. So those are the three properties that can be useful to know, and those are ones that you'll encounter in the next assignment. I want to talk about one more, and this is one that we will discuss in detail. So one additional property is the convolution property of Fourier transforms. Okay, and so what we're going to do is I'm going to first state the problem, like what is it we're trying to solve. Then I'll give you the answer, and then we'll work through the proof. So here's the problem. Suppose that y hat of omega, so some function in the frequency domain, is equal to a product. It could be expressed as a product of two functions in the frequency domain. So x1 hat of omega and x2 hat of omega. So in words, y hat can be expressed as a product of two functions of omega. Okay, so if that's true, then the question is, what is the inverse Fourier transform of y hat of omega? Okay, so if we were to take the inverse Fourier transform of a product of two functions of omega, what do we get? And the answer is not that we get x1 of t times x2 of t, okay? But we'll try to work out what it is. Mathematically, what we're trying to work out is y of t is the inverse Fourier transform of y hat of omega, but y hat of omega is a product of these two functions of omega, x1 hat and x2 hat. And so what we want to know is, what does that equal? Okay, so let me just give you the answer. The answer is that if we were to evaluate this inverse Fourier transform, what we would get is something expressed as an integral. And so it's x1 of tau. So the x1 without the hat means that this is x1 in the time domain times x2 of t minus tau integrated over tau from minus infinity to plus infinity. And so it turns out that if we just made a change of variables, we could show that this is identical to x2 of tau times x1 of t minus tau d tau. In other words, the order of the product of these two functions doesn't matter. It doesn't matter if it's x1 of tau or x2 of tau, and vice versa for x1 of t minus tau and x2 of t minus tau. Okay, so just to be explicit, the the meaning of x1 without the hat, where x1 of t is the inverse Fourier transform of x1 hat of omega, and x2 of t is equal to the inverse Fourier transform of x2 hat of omega. So we're imagining that we know the forms of these functions of omega, so that if we evaluated the Fourier transform, the inverse Fourier transforms, we would get the time dependence x1 of t and x2 of t. Okay, so these two integrals that I've written above are equivalent. So the two integrals above are equivalent. And so I think you could show pretty easily that they're just related by a change of variables. And they define what's called the convolution of x1 of t and x2 of t. Okay, and so there's been a special notation that's been created for convolutions, and I want to show you what that is. The convolution has a special notation, and it looks like this. So x1 of t star x2 of t would be read as the convolution of x1 and x2. And so let's just emphasize first off that this is not multiplication. It's just a shorthand notation for the integrals that were written above. It's this x1 of tau times x2 of t minus tau integrated over tau, which is equivalent to x2 of tau times x1 of t minus tau integrated over tau. Okay, and so if we summarize all of these results, the convolution theorem can be stated as follows. Theorem is, okay, so if y hat of omega can be expressed as the product of two functions of omega, x1 hat and x2 hat, then y of t, which is the inverse Fourier transform of y hat of omega, is equal to the convolution of x1 and x2. And so this is the theorem that we're going to try to prove. Okay, and so let's just get right into it. Proof. So what we're going to do is we're actually going to start with y of t expressed as the convolution of x1 and x2. Okay, and so we're going to start with this y of t, and we're going to take, and then take the Fourier transform. To construct y hat of omega. Okay, and if we do that, and we end up showing that the y hat of omega that we get is the product of x1 hat and x2 hat, then we will have proved our theorem. Okay, and so that's the goal. So we're just going to do that explicitly. We're going to express the Fourier transform of y of t, which is just the integral from minus infinity to plus infinity of y of t e to the minus I omega t dt. And what we'll do is we'll just take this integral and sub it in for y of t. Okay, so we're going to end up with a double integral. One integral is going to be over the variable t, so that's the Fourier transform, and then the other integral is going to be over the variable tau, which is the convolution. Okay, and so we start with our integral over t, and then we sub in our y of t function. What I'm going to do is I'm going to try to match the two integrals with the dt and d tau using colors, just so we can try to keep that as straight as possible. So this red integral is the integral over tau, and so it's an integral of x1 of tau, x2 of t minus tau, and then I'm going to put the d tau in red. And then for our Fourier transform, we still have an e to the minus I omega t, and then we integrate over t. Okay, so the next step is to kind of move some parts around. And so what we're going to do is we're going to reverse the order, or we're going to swap the order of integration. I'm going to take this integral over tau and the x1 of tau, and I'm going to move it outside of the integral over t. I can do that as long as what I pull out of the t integral doesn't have any time dependence in it. Okay, and then this d tau will be moved outside here. All right, so in words, what we're going to do is we're going to switch the order of integration, and this is valid provided anything that's moved outside of the time integral doesn't have any explicit time dependence. Anything pulled out of the dt integral does not have a dependence on time. Okay, so let's see what that looks like. What we're calculating is, y hat of omega is equal to, and so I'm going to try to stick to my color scheme here. So we're moving the tau integral outside, so we're going to have an integral from minus infinity to plus infinity, and we're going to take along with us the x1 of tau, so its explicit dependence is on tau, not on t, so we can make that move. And then what we have is the integral from minus infinity to plus infinity over time t, and then we have a x2 of t minus tau. We have an e to the minus I omega t, and we have a dt, and then we moved our d tau to the outside. Okay, so that's our first step. The next step is going to make a change of variables. So we make a substitution, and the substitution we're going to make is u is t minus tau, and we'll make that substitution in the dt integral. Okay, and so let's note that if u is equal to t minus tau, then t is equal to u plus tau, and dt is equal to du. Okay, so we have y hat of omega is equal to we still have our tau integral. That doesn't change. We still have x1 of tau. And so now we're going to have this integral. We're going to make a change of variables. Instead of integrating over t, it's going to be an integral over u. So originally we had x2 of t minus tau. But with our substitution, u is equal to t minus tau. So this is x2 of u. E to the minus I omega times t. But with the substitution that we're making, t is equal to u plus tau, and then the dt becomes a du, and then we still have our d tau on the outside. Okay. So what we're going to do next is we're going to separate the exponential. So right now we have e to the minus I times omega, and then times u plus tau. So we could write that as e to the minus I omega u times e to the minus I omega tau, and that is what we'll do. And in addition to doing that, we'll rearrange some of the factors. And so again, we can move factors around as long as, say, we don't pull anything out of the u integral that has a u dependence on it. Okay, so this y hat of omega is going to be equal to the integral from minus infinity to infinity of x1 of tau. And then when we separate the exponential, we'll have e to the I omega times tau, e to the minus I omega times tau. We can take that out of the u integral. So we have e to the minus I omega times tau. And then we have the integral from minus infinity to plus infinity. This is now an integral over u. We have x2 of u. And the remaining bit of the exponential is e to the minus I omega times u. Then we have a du. And we have our d tau. Okay, basically the last step we're going to do is we're going to take that d tau and we're going to move it to be just at the end of the d tau integral and before the du integral. Okay, so therefore y hat of omega is equal to the integral of minus infinity to infinity. Now I'll write this entire integral in red. So we have a x1 of tau e to the minus I omega tau d tau. And then all the stuff that's left over is this integral from minus infinity to infinity of x2 of u e to the minus I omega u du. And so you may recognize some of this stuff. This, by definition, is the Fourier transform of x1. And the result is going to be x1 hat of omega. And the black integral is by definition the Fourier transform of x2. And the result is x2 hat of omega. And so therefore, what we've shown is y hat of omega, which if we go all the way back to the beginning, right, so y hat of omega is equal to, sorry, let's slow down. Y hat of omega is equal to x1 hat of omega times x2 hat of omega. Okay, so that means if we were to take the Fourier transform of all of this stuff, the inverse Fourier transform, the inverse Fourier transform of this product of functions of omega is also the inverse Fourier transform of y hat of omega, which is y of t. But now let's go back and look at what y of t was. Y of t was defined to be originally the convolution of x1 and x2. And so what we have then is that x1 of t convolution with x2 of t. And so that is equivalent to our convolution theorem. So what it says is if you have a product of functions of omega and you take the inverse Fourier transform, you'll get the convolution of x1 of t and x2 of t. So in words, the inverse Fourier transform of the product x1 hat of omega and x2 hat of omega results in the convolution of x1 of t and x2 of t. Okay, good. Just to finish off, I'm going to propose an exercise for a student. So an exercise for the student. What we did at the beginning of this is we imagined that we had a product of two functions of frequency, and then we wanted to know what is the inverse Fourier transform. And the answer was it resulted in this convolution of the two functions of time. We could do the opposite. We could say, what if we start with a y of t that's a product of two functions of time? What happens when we take the Fourier transform of that? Okay, so the exercise is, suppose y of t is equal to x1 of t times x2 of t. Then what is the Fourier transform, which would yield y hat of omega? What's the result of that Fourier transform? So the answer is that y hat of omega is going to be equal to, as you probably could have guessed, the convolution of x1 hat of omega and x2 hat of omega. But there's one subtle little difference. There's a prefactor of 1 over 2 pi. And so the challenge is for you to prove that to yourself. You could follow a method that's very, very similar to the one we just worked through above. Okay, so a related theorem is that the Fourier transform of the product x1 times x2, both functions of time, results in the convolution of x1 hat of omega and x2 hat of omega. So that this is all to within a factor of 1 over 2 pi. Okay, so in a future video, maybe about 3 videos down the road, we're going to come back to these convolution theorems and make use of them, and they're going to be very useful when we try to solve a particular problem. And the problem that we're going to try to solve is, if we know something about the properties of transmission lines in the frequency domain, which we do because that's what we worked out in when we were talking about transmission lines. We ended up with this wave equation, which was hard to solve in general, but was something we could make progress on if we assumed a harmonic time dependence, so a time dependence of e to the I omega t. And so when we make that kind of assumption, then we enter into this frequency domain. So everything we did from that point on was a function of omega. So what we could do now is we could take inverse Fourier transforms to learn something about how voltages and currents in transmission lines depend on what their time dependence is. And when we work on that problem, this convolution theorem will be very useful. Okay, so that's where I'm going to stop. Thank you very much, and we'll see you next time.